far we have seen what shell energy balance is, and we have seen the boundary conditions which are required to solve any question. Now we will be seeing the application of this through a question. We have a question over here. Consider electric wire of circular cross-section area of with radius r and electrical conductivity Ke with units ohm inverse centimeter inverse. Through this wire, there is electric current with current density I ampere per centimeter square. The transmission of electric current is an irreversible process, and some electric energy is converted into thermal energy. The rate of heat production per unit volume is given by the expression Se equal to I square by Ke, where I equal to Ke into E by L. Here E is the voltage drop over the length L. Now, if the surface temperature of wire is maintained at temperature T naught and the temperature variation is small to have effect on thermal conductivity K and electrical conductivity K. We now need to derive the temperature profile and heat flux profile equation using shell energy balance approach. So this is our question.
Okay, so in the question we have been given an electric wire through which current is flowing. So this current generates and this current is converted into heat. Some of this current, electrical energy. Now this heat production, the rate of heat production per unit volume we have been given in the question, that is SE, that is equals to I square by KE. Now what is KE? KE is the electrical conductivity K that is given in the question above. Now we have also been given the relation of I with voltage drop and length. Now this is I is equals to K into E by L. Now E is the voltage drop here and L is the length. Now the main point to be noted here is that we have been given the surface temperature of the wire is maintained at temperature T naught. Now from this we will be able to get a boundary condition. That is, at the surface we have been given temperature is maintained at T naught at its constant. Now we have to find out the temperature profile, the heat flux profile using cell energy balance. So first, how will we start this question? So so in the question we have been given an electrical wire of circular cross section with radius r. So the first step in shell balance is we have to choose the coordinate system. So according to the question, we will choose cylindrical coordinate system. Now, in cylindrical coordinate system, we have got three things. One is r, one is theta, and one is z. So this is r. And now we have to see the temperature varies in which of these three. So first we'll see Z. So in the question we have been given that uniform heat production by electrical heating. It is given uniform heat production. This indicates that temperature is not changing in Z direction. Is not changing in Z. Next is theta. So we have to see whether temperature is changing in theta. But as the problem is symmetric around theta, so temperature will not change around theta also. Now we have got only one remaining, that is R. So temperature changes as a function of R.
So now we will be seeing how shell energy balance equation is being applied to this question. We will be seeing each and every term one by one. So our first term is rate of energy in by convective transfer. This term will be 0. Why? It is 0 because there is no actually bulk fluid. The heat transferred is because of two reasons, either due to conduction and convection. We have only solid wire and only conduction is taking place. We do not have any bulk fluid outside the wire. Due to that, our convection will be 0. So at first term and second term, that is energy in and energy out, both will become zero. Coming to the third term, rate of energy in by molecular transport, it will be zero. It will be non-zero. As well as the fourth term, rate of energy out by molecular transport, this will also be non-zero term because conduction is taking place. Coming to the fifth term, rate of work done on system by molecular transport. This will also be zero. Why? Here, molecular transport does not mean actually the molecular transport we have seen above. It is slightly similar to the convection part. How? This term basically implies that the energy is coming into the system due to the molecule movement. Since we do not have any fluid outside the solid wire, there is no molecule moving or energy coming into the system. So this term will be zero. Similarly, the other term, the rate of work done by system by molecular transport, this will also become zero. Coming to the seventh term, that is rate of work done on system by external forces. Now we know that there is no external forces acting on a system. So this term will also become zero. Last term is rate of energy production. This will be there and it will be the whole combined equal to zero. So now our complete equation simplifies to rate of energy in by molecular transport minus rate of energy out by molecular transport plus rate of energy production. This all equal to zero. So now our final energy balance equation comes up to rate of energy in by molecular transport minus rate of energy out by molecular transport plus rate of energy production. All this equals to zero. Now, we are talking about rate everywhere. What is rate? Rate equals to flux into area. So, if we see at the boundary R, the flux going into the system will be QR at boundary R, and flux going out of the system will be QR at boundary R plus delta R. So, now we'll be seeing the rates. Rate of heat in across cylindrical surface at R. This will be equal to the surface area and the flux, which is surface area will be what? It will be 2 pi RL. L is the length of our cylindrical wire and the flux will be at R boundary will be QR at R. So our term will be 2 pi RL QR at R. Second term will be rate of heat out across cylindrical surface at boundary R plus delta. It is also similar to the above one. Our surface area will be 2 pi multiplied by r plus delta r. Here radius will become r plus delta r multiplied by L into flux at boundary r plus delta r, that is QR at r plus delta r. Now we will be seeing at the energy production wala rate. Rate of thermal energy production. Now here we know delta R is almost negligible. So this term will simplify to 2 pi R L Q R at boundary R plus delta R. Now rate of thermal energy production by electrical dissipation will be equal to SE into volume. SE is what? SE is heat production per unit volume. So our volume of the system over here will be pi R plus delta R the whole square multiplied by L minus pi R square L. We will be simplifying this equation now and opening the square system. What we will be getting is pi R square L plus pi R delta R square L plus 2 pi R delta R L minus pi R square L. Our terms will get cancelled out. Pi R square L and pi R square L will get cancelled out. And what we will be remain with 2 pi R L delta R AC. This will be a total rate of heat production.
Okay, now moving further, now the shell energy balance which we wrote earlier, energy balance. Now all the terms we have got, rate of energy in the molecular transport is given by this one, rate of heat in across cylindrical surface. Why? Because rate of energy in, that is QR is going in and QR plus delta R is getting out. So the second term, rate of energy out, that will be a delta R plus delta R, which we have also got 2 pi R L QR R plus delta R. And the third term, rate of energy production, this also we have got by the rate of thermal energy production by electrical dissipation, that is equals to 2 pi R into delta R into L into SE. Now we have got all the terms, that is 2 pi R L Q R at R minus 2 pi R L Q R at R plus delta R plus 2 pi R delta R into L whole into SE. This all is equals to 0. Now we have to rearrange these equations. Now for rearranging, we have got three important things to keep in mind while rearranging. Yes, so while rearranging, we have to keep some things in mind. The first one is that all the differential thickness, here we have got delta R, the differential thickness, should come in denominator. So for by this condition, we get that we have to divide the whole equation by 2 pi R L. Sorry, 2 pi R delta R into L. But here we have to notice one thing also, that we do not have to change the location of any property that is changing with R. And here R is itself changing, so we cannot divide it by R. So we have to divide it by 2 pi delta R into L. The second thing we have to keep in mind is that we have to rearrange such that all the constants will come in HRS, will come in sorry, RHS. Okay. And the third one is that we want the final function to be of the form x plus delta x minus x. That is in this case R plus delta R minus r. So for this, we have to multiply the whole equation by minus 1. So we have got three things to do. First, we'll divide the equation by 2 pi into delta r, 2 pi delta r L. So what will you get now? 2, so dividing also 2 pi r L q r at r divided by 2 pi delta r into L minus 2 pi r L q r plus delta r divided by 2 pi delta r into L plus 2 pi r delta r L into SE divided by 2 pi delta r into L equals to 0. Now what will you get from here? 2 pi gets cancelled, 2 pi gets cancelled, 2 pi gets cancelled. L, 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 delta, delta. So we are left with R, Q, R at R minus R, Q, R at R plus delta R plus R, S, E is equals to 0. But now as stated in the third condition that we want R plus delta R minus R. We want it in this form. So now we'll multiply this equation by minus 1. What will we get? R, Q, R plus delta R minus R, Q, R at R minus R, S, C is equals to 0. Oh, sorry, 1 second. R, Q, R delta R by delta R by delta R. Okay. So, yes. Now, the second condition, that is all the constants will come in RHS. Now, what is the constants here? We have got one constant. So, now the final equation we'll get is R, Q, R plus delta R by delta R. 1 second. R, Q, R at R is equals to R, S, E. Okay. So now you will ask me, why did I divide it by 2 pi delta R into L? Why did I want the differential to come in the denominator? So basically, we'll be going to use the differential form in this. So after using differential form, so what is differential form? Okay, now, so we divided this by delta R to get it in the differential form. Now, what is the differential form? So limit delta R tends to 0, R, Q, R at R plus delta R minus R, Q, R at R divided by delta R equals to d by dr of R, Q, R. So this is, we wanted to get it in this form, so that's why we divided it by delta R. Now d by dr of R, Q, R is S, E, R from this equation. Now, next you have to do is to integrating and rearranging the equation. So by integrating, we will get R, Q, R equals S, E, R square by 2 plus some constant C1. Now this further simplifies to Q, R equals S, E, R by 2 plus C1 by